go.
Tonight, our main speaker is Hanson. He started off his college career studying orchestral conducting and voice at the Boston Conservatory of Music. He then changed his major to science after transferring to Oakland University. He continued a relationship he had established with NASA and worked on asteroid triangulation and pursued areas of radiation-induced damage to DNA. He's majoring in biochemistry and health science, minoring in physics, and about to start his senior year. Plans to apply to medical schools in hopes of continuing this work in conjunction with NASA. Cameron is also president of the Astronomical and Planetary Society at Oakland University. And he enjoys spending his spare time with his wife, his family, 4 dogs, flying Cessnas, music, and making things. His presentation tonight, let me see if it's changed. Radiation in space, mechanisms of damage to DNA, and protection for astronauts.
So, like I said, my name is Hanson, and basically we'll be talking about radiation in space. So what constitutes radiation in space? What are the biggest concerns that astronauts face? Damage specifically as it applies to DNA, and the most recent ways that NASA is proposing that we deal with this. So just a little bit more on my background. I actually got started in through all of this at NASA's Open Innovation Program. Basically anybody could submit an idea or plan for any one of the topics they had. I chose asteroid triangulation, and they got selected at the local, national, and was a global finalist. And then some folks at Glenn Research Center helped me develop this a little bit further, and then some scientists at JPL actually used this for an astrobiology study. And so I was really lucky to have that opportunity, and then when I came to OU, I got involved in their DNA research program. And right now we're primarily focusing on damage to DNA from irradiation, both from a protective standpoint and an increasing damage standpoint. And we're working right now with Notre Dame University, and quite recently we got some funding from NASA to help develop nanoparticles as radioprotectors, which we'll talk about, which is one of the more promising things as far as protection against radiation. Some background on our lab. We have over 300 NIH-funded publications. These are some of the journals that we publish in, and 4,000 citations. Our lab is actually the most prolific lab in DNA research in the world. We have Michael Sevilla, Dr. Michael Sevilla. He heads the program there, and they just do absolutely fantastic work. So, with that in mind, we'll kind of jump into first some basic definitions. So this is an atom, and in the center is the nucleus, right? So we have our neutrons and we have our protons. Protons are a positively charged subatomic particle. Neutrons are neutral, and then surrounding it in orbit are the electrons. And electrons are one of the few things in the universe that are truly magic, because they can go from here to here without going from here to here. It's something called quantum tunneling. And so they don't actually orbit the nucleus, but they surround it in a cloud of probability. And 99, it's endlessly fascinating. And 99% of all chemical reactions that ever take place only deal with the electrons, the exchange of electrons, transferring, and all that kind of stuff. So when we think about radiation, radiation is a physics term that basically describes the transformation, the emission and transference of energy in a wave or particle form. And UV light is sort of at the breaking point from which we consider safe, which is non-ionizing radiation. That's radio waves, cell phone things, microwaves. Microwaves, the only exception with that is that the frequency will actually oscillate the hydrogen and oxygen bonds between them, and that will create heat. So the microwave itself doesn't really do the damage, but the heat creating can do harm to biological cells. But otherwise, we consider everything below ultraviolet safe. Everything above ultraviolet is what is called ionizing radiation. Ionizing radiation means that it has enough energy to remove electron from a molecule, thus ionizing it. So when we think about damaging ionizing radiation, the main things we think about are alpha radiation, beta radiation, and gamma radiation. Now, radiation's damage is caused primarily from depositing the energy of the kinetic particle into a tissue or material. And the main forms are, like I said, alpha, beta, and gamma. So this is alpha radiation. It is part of radioactive decay, and it's basically an ejection of a helium nucleus. So we can look at something like radon here. It decays into polonium, which is 2 elements down as far as atomic numbers go, but it loses 4 mass numbers into helium. And then it also gives off something called gamma, which we'll talk about. So alpha radiation is the least penetrating of all the ionizing radiations. It pretty much can't pass through skin, clothing, and stuff like that. It's mostly damaging if it's inhaled or gets in contact with the mucous membrane, because it interacts with the water in the cells on that level, and all the energy is deposited at once. So once you're hit by an alpha radiation, you are no longer radioactive. It dissipates, all of its energy is gone. The next is beta radiation. Now beta comes in 2 forms, which is positive and negative. And basically, this is an ejection of a fast-moving positron or electron. Positive is the positive radiation, and electron is the negative. So with beta minus, it converts a neutron into a proton. So you take something like carbon-14, a neutron becomes a proton, it becomes nitrogen, and it ejects an electron. Beta positive converts a proton into a neutron. So this is what we talk about when we do PET scans. Now, PET scans use something called fluorodextroglucose, which is a radioactive form of glucose and fluorine, and it's taken up by high metabolic areas, things like tumors and stuff like that. So patients given this, and it will eject positrons from it. Now, when a positron meets an electron, they annihilate each other, and they give off gamma radiation. So we pick off that radiation, and that gives a signal. Now, beta radiation, because they're smaller, they're more penetrating and slightly more damaging, but the ultimate damaging form is gamma radiation. Gamma radiation is highly energetic photons. So you get something like cobalt, and it decays into an excited state of nickel. And then that gives off an electron and gamma rays, and then that excited nickel gives off a gamma ray and becomes its ground state. So what does that kind of mean? Well, where we get light is basically, this is the spectra of hydrogen. So as we see, the higher the energy shell, these electrons move up. All electrons want to exist in their comfortable shell at their lowest ground state. So when they're pushed outwards, they want to fall back in, and when they fall back in, they give off energy. And so as we can see, if we move past blue on that side, then we start getting into the ionizing radiation, things like X-rays and gamma rays and things like that, and then the other way. So the higher the energy level goes, the more it shifts down the electromagnetic spectrum to damaging things. And so you can imagine that if you push it high enough, it'll get to the ultimate form of the electromagnetic spectrum, which is gamma radiation. Gamma radiations are like microwaves, visible light, X-rays, all of these things are waves. But interestingly, they behave as a wave and a particle. It's called wave-particle duality. And so they often accompany beta and alpha radiation. They're deeply penetrating because of their size, and they scatter. something called the Compton effect, where it interacts with matter and it basically ricochets like a bullet inside of your cell. It causes secondary damage via electron dissociation and attachment, which we'll talk about. And it's basically, as the name implies, it knocks out an electron. That electron wants to attach to something else, and it does, and it forms a free radical, especially in DNA. Less ionizing than alpha and beta, but it's more penetrating, so therefore it's considered more damaging. So what are the greatest risks that astronauts face? Well, cosmic radiation and energetic particles from the sun and the universe, traveling at near the speed of light. So these are things like protons. And so when we treat tumors here on Earth, we use proton beam therapy. That's shooting an ionized proton, and obviously that does a fair bit amount of damage. And cosmic radiation, as we can see, this is a normal cosmic ray. It's comprised mostly of these gamma areas here, electron area here. Here's the positron, which we talked about, and then gamma and gamma. And then the the positron here turns into gamma because it presumably interacts with one of the tens of trillions of normal electrons which exist in our atmosphere and our cells. So cosmic rays are continuous. They just flood the universe. Most spacecraft in low Earth orbit, which we'll look at in a little bit, are protected by the Earth's magnetic field, because if you think about things that have a charges and magnetic fields repel each other. That's how magnetism works, and so we're pretty much protected by that, although some of the stronger ones are able to penetrate through. Some of the larger ionized particles are anywhere from a proton to a uranium nucleus, all ionized, so very damaging. And they come from both inside our solar system and outside. The heavier ones are pretty much from the death of stars and things like that. The heavy elements also cause something called heavy ion tract damage, which is the most devastating form in and of itself that's not caused by secondary interactions. So solar radiation. Obviously, we have solar flares like this, and it's mostly comprised of ionized hydrogen and helium traveling at near the speed of light. It's localized, which is relatively good because it's not widespread, and if we can time it right, we can avoid these solar flares. The problem is at maximum we have around 48 hours to predict these things. X-rays are the primary form of electromagnetic radiation. Now the only thing that differs between gamma radiation and X-ray radiation is where they come from. Gamma radiation comes from inside of the nucleus, and the X-ray comes from outside, so the interaction with the electrons. But the effect it has, which we'll call LET, or linear energy transfer, is the same. It affects cells pretty much the same way. So when we think about that, size obviously matters, and so does direction. So anything in that path is pretty much going to get a deadly dose of radiation immediately. So it's important that we figure out a good way of predicting where and when these things are going to occur. So now my favorite, favorite's kind of misleading because I don't enjoy this, but I think it's really interesting. So damage to DNA, this is what all my research is about. And basically we have two forms of interaction. We have the interaction between the radiation particle itself and the DNA. That would be the top one, where the X-ray comes in, interacts with the DNA base, causes damage. And then there's heavy ion tract, which these are things like the protons all the way up to uranium. And what these do is they actually cause dissociation of your DNA bases. They break apart your DNA, which causes the DNA strand to, be pretty much unrepairable. And once you get it to the point where it's unrepairable enough, then your body cannot handle it, and so it basically will uncontrollably divide, and that's where we get cancer. So how do we study these things here? We use two techniques primarily. Free radicals, we use something called electron spin resonance, also sometimes called electroparamagnetic resonance. And this is really good for studying individual radicals and where they are. For things that are on a larger scale, we use high-performance liquid chromatography, which is just another form of chromatography. And then that gives us our DNA base yield, which we'll talk about. So when we think about radicals, there are two ways that a bond can be separated. It can be separated heterolytically, meaning all the electrons go to one and then the other one gets none, or it can be broken in half. And this takes a little bit more energy, which is why we need light or gamma radiation or something like this. And so we have these two, this is hydrochloric acid or hydrogen chloride. So now we have these two pairs, each without an electron pair, so each with a free radical. And these are particularly damaging, as we'll talk about, because through something called propagation, it will continue. So this electron will rip off a proton from that one. So now that chlorine will rip off from the hydrogen, so now that one's happy, but now it's left another radical. And it will do it to another stable molecule, and it will create another radical. And so this chain will happen until it finds another radical or another electron that it can pair to, and then it's happy, and then it stops. So ESR, this is sort of the principle behind ESR. I won't get too much into it, but basically we put this unpaired electron into a strong magnetic field. And when we do, it will flip. It'll do something that we can get into a spectra that looks like this. So it probably doesn't look like much, but through this we can actually tell where the electron is, what this one is, how it evolves. The cool thing about ESR is it's all done at liquid nitrogen temperatures. So it's done at 77 Kelvin, pretty cold. And then when we warm it up, we can see where the interaction goes, how it affects with its environment, and all this stuff. So it's very interesting for individual radicals. So here are our DNA bases. On top, we have our purines, adenine and guanine. And then on bottom, we have our pyrimidines, uracil, thymine, and cytosine. So, believe it or not, these are actually extremely electrophilic, which means they love electrons, which is a problem if you have a bunch of free radicals and free electrons in your system, because they will readily take it on, and then they will give it to somebody else, causing other damage and stuff like that. So, just to give an idea, this is guanine and thymine, and each dot here, 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 these are all the radicals for just two of our DNA bases. Down there, these are the sugars that are, so when we think of deoxyribose nucleic acids, the nucleic acids are guanine and thymine, and then the deoxyribose are our sugar. So these are all the radicals that can be formed, and then radicals will undergo abstraction. So they'll take things and they'll rip things off. So the two major ways that this happens is direct interaction and indirect interaction. Direct interaction we kind of already talked about, which is the radiation's effect directly to the molecule. Indirect effect is by far and away the most prevalent and the most damaging effects that radiation has. So radiation causes free radicals, primarily through water and oxygen, and then these free radicals scavenge and rip apart our DNA. Now, it's increased by oxygen by this. So we irradiate oxygen, which is obviously in our bloodstream and our cells, and this creates the peroxide radical. This is the ultimate radical. This will pretty much destroy anything that it comes by, and it will do so again and again and again. So when we think about high damage to DNA, this is our guy right there. And then when we're in water, this is our guy, hydroxyl radical. That is the same thing. It's not as strong, but it will pretty much destroy anything around it. High linear energy transfer. That basically just means the interaction between the radiation and its environment, in this case, DNA. So ionized particles like those produced by solar flares and cosmic radiations will cause these bases to basically pop off, in which we talked about base yield. So guanine, adenine, thymine, and cytosine. So what we do is we take a normal thing of DNA, and it's completely homogenized, normal, and then we irradiate it. And what we see with our HPLC is this. So all the bases have popped off their strand and are now completely separated. Now obviously that's not very useful for us. We can't use things individually, we need them in sequence in our genes. So this is a big problem, but this is how we detect it. So, when we think about protection, we have protection from our Earth and our orbit. Now, this is the full thing, so we'll zoom up on this a little bit right there, which is, this blue here is called low Earth orbit. And as you can see, pretty much everything we do happens in low Earth orbit, which is about 12,000 miles above our surface. The next one is MEO, medium Earth orbit. And as you can see, the moon is just on the outskirts of that. And the farther we get out from that, the less protection we have from our magnetic field. Our magnetic field is relatively small as far as magnetism goes. It's about 25 to 65 microteslas. And to give that, some varying in MRI, for example, is about 3 to 5 million microteslas. So it's a weak magnetic field, but it works. It works really, really well. The total field extends about 370 miles outside, 273,000 miles outside of the Earth, which is good because the moon is 238,000 miles, so it's in it, but weakly. But we measure all this using these dummies here. These dummies here use it's called tissue equivalent plastics, which we'll talk about, and they measure the amount of radiation absorbed in space and the ISS in particular. The average stay for the ISS is 6 months because of the risks one would face with that high level of radiation. Although Scott Kelly right now, as I'm sure you all know, is staying 12 months. So scientists will surely be studying his cells and studying his DNA and any adverse effects that happen with his. So radiation doses. Here is the 6 months average, which is approximately about 100 millisieverts. So we'll just say MSVs. Now as you can see, that's a lot more than the Department of Energy's radiation worker annual limit. And it's funny. So it's more damaging, but it's still within the realm of not deadly initially. So when we talk about that, we talk about the highest radiation concentration at Fukushima was about 400. So we're right around here. So this is at the level that cancer is first starting to get noticed. It's still more than what the Department of Energy says is safe, but in the name of science, we move past that. And these are kind of the effects radiation has. So in high doses, it can cause cataracts. This is the particular interest. The lungs are very vulnerable because of the mucous membranes. And we talked about the radiation's effects are maximized by the presence of water and things like that. Mucous membrane has a ton of that. So that's a major problem that we have. So to the moon. Moon timing is everything. So the Earth's magnetic field, as we talked about, extends about 370,000 miles. The moon is weakly in it. But it's right in between our higher orbit and our lower, or our medium Earth orbit. But there's something called a magnetic bow shock. Now the magnetic bow shock is when a particularly strong force will push back our field. And when it pushes back our field, obviously we have less protection. And it can push it back to about 90,000 miles. So obviously the moon would be far outside of that. The other problem we have to consider is the magnetotail. So when charged particles, like these ions, like protons and things like that, hit this, they will follow these magnetic tails because it's like following a magnetic current. And so if we have something here or within these magnetotails, it'll basically be like a proton beam. It'll shoot them at you much more than you would if you were in these protected areas here. And actually between the Apollo 16 and 17 mission, the largest solar prominence event happened, and it was recorded at sufficient levels that within 10 hours of the start, every astronaut would have been killed with lethal doses of radiation. So this is why the protection side is very important. So what about outside of Earth's magnetic field? So we think about Mars and deep space. Obviously the most feasible and the most concerning is Mars. So the journey to Mars as it stands right now is about 200 to 300 days. And with our current technology, it's 35 million miles away. And it has some protection of its own, but it's pretty spotty, as we'll look at, and the biggest concern is the actual journey itself. So we have these things called RADs, radiation assessment detectors. They're on Curiosity, the rover, and they were on the whole time that it was flying, detecting on what these levels of radiation would actually be. 95% of these are actually due to cosmic radiations. And not a whole lot is actually due from our sun. Again, it all has to do with timing and where those things are going. The fact that it would hit the precise location of where the rover was, relatively rare. So we mostly think about cosmic rays, which are comprised of gamma radiation. The estimated radiation exposure in one trip would be about 400 millisieverts. So that's obviously much higher than what the Department of Energy says is safe. With a large solar event, dose can be lethal within minutes. Anything over 10,000 millisieverts is lethal almost immediately. As we can see here, our annual cosmic radiation, mostly due to radon, things like that, pretty low. So here's our 6 months trip to Mars. We're at about 400 to 500 millisieverts. Again, much more than what the Department of Energy says is safe. So when we think about that, we're right around here. And obviously, like I said, any major solar event will push it up here, which is acute radiation sickness, kill somebody within a month, all these kind of things. Now, with this being moderate risk, I mean, it's moderate, but it's not moderate. I mean, there are certain things here where it's detectable of cancers. So anything up here is, it's pretty much guaranteed that it will affect your cells in some way, which is bad. Martian surface. So on the surface of Mars, as we see, here's Earth's magnetic field. It's very continuous, it's very homogeneous in these areas. This is Mars's remnants of its magnetic field. It doesn't have an iron core like that's moving to keep it going, so it has these little spots of weakly magnetic. So it's not anything that would really protect us. The atmosphere is pretty weak, so when radiation comes down, it won't scatter because our atmosphere has oxygen. Oxygen will fuse together, create ozone, things like that, something to absorb the radiation. Mars doesn't really have that. In fact, it's like that much. It's about 0.67 millisieverts per day. So that's like getting 6 X-rays a day on the surface of Mars. Highly variable, and the atmosphere is weak and thin. So what are we going to do to protect ourselves? Well, there's a couple different ways. Right now, NASA does not have a current established plan of what we will do. So everybody's kind of pitching their idea, and my guess is it'll probably be a combination of all of these things. Active radiation shielding, utilizing high-temperature superconducting magnets. So we use superconducting magnets right now. Particle accelerator is an example of those. And those happen at below 4 Kelvin, so liquid helium temperatures. So high temperature, it's not really high temperature, it's still like negative 300 and something degrees Fahrenheit, but it's warmer. It's easier to keep it that cold than it is to keep it at liquid helium temperature. So this is one plan. This one plan is a superconducting magnet. One problem with this is power, spacecraft design. There's no great way of really knowing how it'll interfere with your communications, with health effects and things like that. So there's no, that's an idea. This one I think is a little bit better. This one uses plasma. So plasma is a charged liquid or gas, and you put it through a tube, and anytime that you have a charged anything moving, it'll create a magnetic field. So with this, if you remember from physics class, you can use the right-hand rule. And so your magnetic field comes out that, you'd circle it that way. And so basically you would create this artificial plasma-induced magnetic field. This is better because it's lighter, it requires less power, and it's relatively compact. So that's a pretty good idea. So here's a laboratory design of it, and it actually works in the lab, which is good. So the issues with that is, like I said, it puts a restriction on your spacecraft design. power. You have to worry about how you're going to power these things. Interference with communications and electronics. Human effect on magnetic field proximity. Now, many people get MRIs and they're not affected, so that's probably not a huge concern, but over 6 months, if you're getting an MRI for 6 months, it might cause some effects. So that would be something that would have to be tested. And then materials for cooling a superconducting magnet. So liquid helium is actually one of the few things that we use for NMR and things like that. That's actually, they predict in about 50 to 60 years, we'll have no more helium left. So there's not an easy way to get helium, we can't harvest it. So that's maybe a concern, especially as the Mars mission is a little bit, about 20 years away, at least. So once on Mars, the magnetic field is much more practical. Then you build up this grid of magnetically charged orbs in this case, and you could power it through solar power or geothermic heat if there's enough of that below. And then this is a better way of doing it. You could create your magnetic field above where you're working, and that's a little bit easier to conceive of than one on a spacecraft. So the other thing is something called A150 or A150. And then other TE plastics. So TE plastics means tissue equivalent plastics. Now we use this sometimes now for protection against people who are getting radiation therapy. So you put it around it and it absorbs almost the same as tissue. And basically what it is, it's a polymer. So you have something like a paraffin, some wax type thing, and then you put it in nylon and then polystyrene, and all these different things combined create a tissue equivalent plastic. Now the cool thing about this is you can conceive that you can line your entire spacecraft with this. And if you are basically shielding the whole thing without the weight of lead and without the constraint of a big magnet and stuff like that. So this is a pretty promising thing that they're actually working with right now. So deployable shields. This is a solar sail, but it's similar to what they would propose. Now this is a weak idea because this takes up a lot of room. If it could be compactly concealed and then deployed when needed, that's probably a little bit better, but it's only useful if you know the direction of the radiation, which for, as they said, 95% of it is cosmic rays, which is continuous. Not really, you're blocking it only on that side. This is more useful for things like solar flares and things like that. Heavy ions that are coming, you could shield your craft through that. Recycled water. So I actually think this is a really cool idea. So normally we have these hollow spaces in between it, which is, all the electrics are fed up and all that kind of stuff. So one of the ideas is that you put human waste in between it. So instead of it just being stored or ejected, you line your craft with this. Now, this is a smart idea because it's light, inflatable cavity like this. You could literally, if you could imagine that you have this inflatable part of your spacecraft that you would inhabit, so you could put more and more and more and more. And so about 7 feet of water is equivalent to 1.2 feet of lead, which is pretty substantial because when radiation interacts with water, like I said, through the Compton effect, it will scatter and it will turn into radicals, and then that will interact with itself. So it's a really good agent at absorbing that radiation. So H2O with organic materials, like body waste, will probably prove to absorb more because it'll have more things to interact with, more things to scavenge those electrons that are free, and everything add up. So you consider adding plastics, body waste, magnetic shields, you're good to go. So predicting solar weather, this is another good idea, but it's really hard to do. Right now, like I said, we have about 2 days warning, 48 hours is the best warning. We don't understand fully why the magnetic field tangles. We know that it's a buildup of magnetism and charged particles, and once they break free, they jettison all of these highly charged particles out. But we still don't understand why they're tangling up. And so, if we could conceive of things mathematically, that's going to be the best way. Our observatory and things like that are right now our best tools at doing this. We are able to detect sunspots and things like that. But the underlying mechanisms of why these things happen, we don't really understand yet. And then finally, chemical protection. This is sort of what I'm working on and I really enjoy. Cerium and carbon nanoparticles. So this is the thing that we recently got NASA funding for. And what our initial research is showing is that if you put cerium and carbon, which are non-reactive, into your cells, into your DNA, and things like that, they actually absorb radiation at a level of almost 50%. So you could imagine if we would put into the cells, someone being affected by radiation would be 50% less likely of getting cancer than someone without this. And then we have something called diethyl dithiocarbonate, which is right there. And this is actually currently used. This is used in vivo, and it's this guy right here. There's your two thios, and there are your ethyls, and your nitrogen. And this is a really, really good electron scavenger. So this prevents free radical formation by scavenging these free radicals. And it's a great proton donor, too. Anything that will donate a proton will be able to get with a free radical and basically neutralize that free radical. So this is showing some real promise. And antioxidants, certain antioxidants are really good at scavenging electrons, scavenging free radicals. And since that's primarily the effect, that would mitigate all of the risks on the indirect, not all the risks, but a majority of the risks on the indirect side. However, you still have the interaction between the radiation particle itself, which is things like these nanoparticles would help with. All of these are considered radioprotectors. When we talk about radiosensitizers, which we use for tumor radiation and things like that, it's things that will increase damage. So when I mentioned my research, I'm focusing mainly on the two forms of protection and maximization of energy. That's why. If you want to maximize it, you want to do it for cancers. If you want to minimize it, it's things like radioprotectors and for astronauts and things like that. So I think that eventually we'll get to the point where it's probably going to be a mix between all of these. I think the superconducting magnet and the plasma magnet have the strongest implications as far as the spacecraft itself. NASA is dumping a ton of money right now into this right there, into radioprotectors at the cellular level. So I think eventually at some point all of these will combine and we'll have a better way of protecting ourselves from radiation, which is great because if we can get it to the point where it's safe for our astronauts, we can get it on Earth. And anybody doing, cancer treatments or things like that, you can isolate tumors so they're not feeling the effect of the radiation throughout their body. They're feeling it in these very targeted areas. So everything involving with radiation becomes safer and it becomes more practical, and and everyone benefits from that.
How are we protecting our astronauts on the space station today?
By keeping them at 6 months, unfortunately. That's our best thing that we're doing. Is every 6 months we rotate our astronauts. We take them from, in 6 months period, it's all staggered, but that's pretty much all we're doing right now, is just rotating the schedule with them.
Don't they have a safe room?
They have some compartments lined with lead, but getting lead up there is pretty hard. And again, you have to have enough lead that it's worth it, that it's worth the extra weight to pull up. And so they have some particular shielding, especially for solar prominences and stuff like that. But most of the time they're not in there. And most of the time they're affected by cosmic radiation, which is, less strong initially, but it's constantly there.
Yeah, just to make the comment, we're getting bombarded with cosmic rays through the building right now.
Oh, no.
There's about 100 per second hitting your body right now.
This kind of akin to what, Dick's question was, but I've read that for projected missions to Mars and beyond, that there would be a safe room, and the safe room might be inside of the fuel tanks or something of that sort. And for the big things like solar flares, where you need maximum protection. Is that part of your thinking, or part of the thinking that you understand?
For sure. But again, most of the time they're not going to be in the safe room, and once they get to the surface, then they're exposed. So they'll presumably build a safe room on there for those type of things.
For the transient events.
Right. And so it's still, even with a safe room, you're still hit with these heavy ions, and those can do it. But absolutely, a safe room is one of the best bets for that type of thing. It's just, you can't really line your entire ship with lead. Otherwise, it'd never get enough,
No more here.
Talking about Scott, the astronaut,
Scott Kelly.
are they doing anything preliminarily for him, or are they just going to let him expose and then figure out how bad it's going to be?
Well, here's a really cool thing about him. He actually has a twin brother.
Yes.
And his twin brother is on Earth, and he's on there. So preliminarily, they did some, just general CAT scans and things like that. They took, all of his vitals and all that kind of stuff. And then they're going to send him up and see what happens. I'm guessing they're probably going to focus on his joints, his muscles, all that kind of stuff, and his eyes, because they found that your eyes change quite a bit. The other thing is that your white blood cells change quite a bit in zero gravity, and they're not really sure why. So
Do they become less protective, the white cells?
They don't know, because they're all pretty much sterile when they go up. No one's really gotten sick up there. So that's probably one of the things they'll be looking at once they return, how vulnerable they are to pathogens now that their cells are changed till they return, or if they return. Yeah.
Cameron, is it your general knowledge, since you know more about this than any of the rest of us in the room, that there is a general consensus that there will be a solution, it's a combination of all the factors you talked about?
Yes.
A solution for see there, Ken?
I think so. I think because NASA feels so, that's why they're dumping so much money on this. I think they believe so, and they've done some pretty good stuff before.
We had a big debate in this group about 3 years ago about, and that was one of the key factors.
Really?
Whether long distance space travel was even possible because of things like this.
I think, and I'm just saying this because I'm part of it, I think the greatest advancements in that area will come chemically, will come from the inside, from radio protectors and things like that. I think that will become one of the most effective.
Maybe I missed a key point, but is there a linear relationship between radiation exposure and DNA damage?
It is linear, yeah. So when you plot out these things, we get these samples of DNA, again, all homogenized, and we do it at varying doses, and we can actually plot a linear.
I was wondering because, especially you're outlining the homo and heterolytic processes, especially the heterolytic would suggest kind of a non-linear relationship.
Yeah, well, the radical formation is non-linear.
Okay.
But as far as the absorbed damage it does, that tends to be linear.
And as far as your chemical scavengers, or however you describe them, you said proton donors and electron acceptors, those would be kind of the classic definition of acids, wouldn't they? So are you
Lewis acids and Lewis bases.
Are you restricted to using acidic media? Or?
Well, the thing with Lewis acids and Lewis bases is they donate electron pairs.
Right.
Right, so we want something that will donate just an electron.
So you're talking about a proton donor, that would be like more like a Bronsted acid, wouldn't it?
Right. So that, yeah, exactly. Right, that's what we want. That would be great at neutralizing radicals and stuff like that. Yeah, exactly.
Yes, Mike.
I was watching a program on uranium recently on PBS, and I think the normal background radiation is like 0.2 millisieverts. Is that the measurement? 0.2,
Yeah,
and you said on Mars, on the surface, it's 0.67.
yeah,
Is that an hourly rate?
that is. Let me double check. I think that was it.
And what is it, if say, when you go through the Van Allen belts, in case you know,
I'm sorry, say it.
going through the Van Allen belts, what would that rate be?
That I actually don't know. That's
High.
good question. Presumably high. But yeah, I'm not sure. That's the thing about the radiation also. It's super inconsistent with Mars too. I mean, it depends on the season. It depends on what elevation you're at. And that's what's so hard about tracking the radiation, predicting the radiation, is there are these pockets where it's, you know, much more.
The Apollo astronauts went through the Van Allen belts really fast.
Was it like an hour or two they were through?
I don't remember. I have a question. You showed astronaut living quarters on Mars and structures above them generating magnetic fields to try to protect them. Why wouldn't they just build tunnels and get a couple of yards of dirt above them? That'd be a cheap solution, right?
Absolutely, and actually here's where me and Tony disagree, is I think there's actually life underground. On the surface, there's no way life will exist, there's just too much radiation. But in caves and things like that, I think that's probably the most likely place that we'd find it. But yeah, we could do that, but then you'd need the things to dig, which are, you know, you have to put them on there and somehow. So it's kind of a balancing act between weight and fuel and all that stuff, because that's all my weight is fuel.
Put a net on top of the ground, dig under.
Is the DDC, is that, you give it IV or you give it orally? What's the lifespan of DDC itself? And is that the thing that you're building on, looking for other isotopes of it, et cetera?
So the DDC is,
Because you said you hope that they would be able to take something internally.
right, yeah, exactly. So,
Do you drink this stuff?
no, you don't drink it. It's actually injected into around where you would want to protect. My work primarily focuses on the cerium and carbon nanoparticles because it's such a new thing. We work with just the chemicals themselves, and then we usually leave the biologists to figure out how to get it in. But as far as DDC, they pretty much do site-specific injections. But as far as the cerium carbon nanoparticles go, I would imagine it would have to somehow be adhered to your DNA base, then that would be given to you, and then your DNA replication would take that with it, and then it would be attached with it. I don't think you could, I'm not sure.
How do you give the DDC? Can you swallow
The DDC?
it? Yeah.
Well, right now I think they, from everything that I've read, is pretty much in vitro and in vivo. So it's just injecting it into the cell.
And how long does it stay intact in the body?
That depends, I think, on the enzymes around it, but normal DNA will work itself out as far as the cerium and carbon nanoparticles go. Again, my work is not really with the DDC, but everything that I've read says that it has a finite lifetime that depends on where it's being injected, how metabolically active that area
It
is.
sounds like you got a lot of work to do with that.
I agree.
In other words, if the answers are easy, okay, it's done.
That's right.
That's right.
If you want to donate to our funding, we are too.
Yes.
Probabilistically speaking, Mr. Fantastic or the Thing, which is more likely?
Hulk.
Oh,
No, Mr. Fantastic or the Thing, probably the Thing.
at least lumpiness, yeah.
Yeah, we'll go with the Thing.
Okay, let's thank our speaker again.
Alrighty, well, after our meetings, if you're not on call, we are, many of us go to the Red Coat Tavern on Woodward Avenue, just north of 13 Mile. And if you would like to continue the astronomy with some astronomy, that is where you can go. And otherwise, thank you for coming out. We still have some